Hello, my name is Michael Collins, and this is a pre-recorded presentation for the 2020 International Conference of Cognitive Modeling called Detecting Learning Phases to Improve Performance Prediction. This research was conducted by myself, Michael Collins, Caitlin Tennyson, Kevin Gluck, and John Anderson.
One of the key interests of psychology has been to better understand how individuals acquire and retain information over time. Besides being a fundamental basic science question, this issue has been an area of interest because of its clear correspondence between the research findings and clear applications in the real world in many different areas, such as education and training. In order to better understand human learning, three major factors have been proposed.
These three features of learning are referred to as the power law of learning. So as we gain more practice opportunities on some task, we become more proficient over time. Power law of decay, so as the time between instances of practice increases, our ability to retain that information also decreases. And the spacing effect, so as the exposure, we space out practice opportunities, we learn that information at a slower rate. However, we are able to retain that information over a greater period of time compared to a mass practice schedule where we practice everything at once. So one model in particular that's attempted to account for these three learning characteristics I discussed previously is the predictive performance equation. It's composed of 5 individual equations. And there are 4 fixed parameters. So there's a learning rate, a lag, n coding the number of exposures on some task, and t, time at which that exposure to some item occurred. There are 4 free parameters. There's a decay intercept and a slope. There's a threshold parameter within our logistics term, and A, which represents our prior knowledge of the individual coming into this task. And given these 5 equations, we're accounting for those 3 regularities of learning that I talked about earlier. So there's the power law of decurrent, power law of learning, power law of decay, and the spacing effect. Although the predictive performance equation has been validated across a wide range of both real-world and laboratory studies, one of its limitations is that it assumes performance follows a continuous performance curve. This assumption stems from evaluating aggregate learning curves. An example of this can be seen here, where we look at the average time it takes individuals to solve novel math problems as a function of trials in an experiment, where we see, on average, performance follows a nice power law, and we see consistent improvement over time. However, if we look at the individual variation of individual subjects, we see that there is a great deal of variation across subjects in their ability to learn this information. From the assumption of a continuous performance curve, this individual variation can be seen in one sense as sporadic. However, others have suggested that this sporadic changes in performance are really show refinements of individuals' cognitive process and strategies that they're using to solve these tasks over time. And this idea is really in line with the skill acquisition literature, where it shows that individuals have gone through discrete changes and learning phases in order to acquire competence in some particular skill. One model of skill acquisition in particular is from Tennyson and Anderson, and their model proposes that individuals go through 3 specific learning phases when acquiring a skill. So there's a computational phase where individuals solve a problem by following the steps of some particular algorithm. There's an associative phase where they start to consolidate different parts of that algorithm. And then there's an automatic phase where individuals are simply retrieving from memory the answer to that specific problem. And in general, this theory predicts that performance improvements are seen both within and between phase. Currently, the predictive performance equation has no way of representing these distinct learning phases. And this can lead to problems when the model is taken from applied into average performance to an individual's performance on a specific item, because it's going to interpret the individual variation as noise, leading to invalid out-of-sample predictions. What we need is some method of combining the predictive performance equation with Tennyson and Anderson's skill acquisition model. Recently, Lee 2019 has formalized a fully Bayesian change detection methodology. This methodology has been used to identify performance changes across a range of domains, such as learning in category and associative learning environments, or in decision-making tasks. So in this presentation, I'm going to propose a new model called the TAPT, which is an integration of the 3 different models I've already discussed before. So it's the predictive performance equation, Tennyson-Anderson skill acquisition model, and Lee 2019's change detection methodology. In the rest of this presentation, I'm going to talk about a model evaluation that we conducted, comparing the inferences of learning phase from the TAPT model and the Tennyson-Anderson skill acquisition model, and compare and contrast the predictive performance equation and the tapped model when both calibrating and making predictions of individuals' performance in a learning study. Moving on to our method. The data I'm going to present today was collected from 101 subjects recruited from Amazon Mechanical Turk. All subjects participated in 2 different experimental sessions. So day 1, participants came in and then learned a very set of novel math problems that I'll discuss on the next slide. On the second experimental session, day 3, participants were retested on the learned material from the first experimental session. In this data set, individuals completed a set of novel math problems called pyramid problems. Pyramid problems have 2 parts. So there's a base outlined here in red and a height outlined here in blue. The base of the problem refers to the starting point, and the height refers to how many numbers past the base have to be added to the base. So an example here, so 2, 4 means that individuals have to add 2, 3, 4, 5, 6 for a solution of 20. In the experiment, there are 2 particular important experimental manipulations. The problem height, controlling how difficult the problem was, so 3, 4, 5, 6, how many numbers have to be added to the base, and the spacing schedule. So each item that was learned on day 1 and day 3 was placed on a unique spacing schedule, being shown every 4, 8, 16, or 32 trials. After the data was collected, 3 different models were used to fit and predict data from this experiment. 3 models we compare in this presentation are the Tenson-Anderson skill acquisition model, the predictive performance equation, and finally, TAPT. For Tenson-Anderson's skill acquisition model, we fit a hidden state Markov model with the individual's reaction time data. This hidden state Markov model estimates individuals' transition across different stages during day 1 and day 3. At each trial, the model predicts both what phase, computational, associative, or automatic, that estimates they are in, and then also whether they stay within that particular phase or transition to a new learning phase. The second model used in this study was a Bayesian implementation of the predictive performance equation. This is simply a graphical representation of the same equations I discussed at the beginning of this talk. And for each individual's performance on every pyramid problem during the study, we estimated individual free parameters for their performance. So we took their performance on a particular problem, we calibrated the predictive performance equation to their reaction time data, and then we used those parameters then to make predictions about their performance on the following day. Finally, we have the TAPT model shown here as a Bayesian graphical model. This has a high degree of similarity with the predictive performance equation. However, the main difference being the extension of Lee's change detection methodology right here, which allows us to estimate a unique set of free parameters for all of the data points before and after an inferred change detection approach. So an example of what I mean by this is we can take the same individual's reaction time data, we can calibrate our model to that performance, and then we can look at all the data points before and after an inferred change point. For this individual, there were 3 unique change points estimated. And then we can take the reaction time profiles estimated from Tenson and Anderson's skill acquisition model for each of the 3 learning phases. And then we can classify what phase we think they're in. Here we can see that the TAPT model has classified the individuals going through computational, associative, and automatic phase of learning. And then once we have these learning phase categorizations, we can use this information to make predictions about the next day's performance. So instead of using information from phases that the individual has already gone through, we can make predictions about using information that we've learned about the individual's performance at the highest phase they've obtained. So here we use the parameters from estimated from when the individual's in the automatic phase to make predictions about their day 3 performance here. So next we'll be moving on to our results. So in the results I'm going to discuss here today, we really had 2 major questions. So one, we wanted to compare the inferences of learning phase between the TAPT model and Tenson-Anderson's hidden state Markov model to compare if they're making similar inferences on the individual's learning profiles. Next, we wanted to compare the TAPT model to the predictive performance equation both in their ability to account for an individual's performance across a set of learned pyramid problems during day 1, and evaluate how well they were able to predict performance on day 3. To address this first question, we plotted the proportion of learning phases, computational, associative, and autonomous, estimated by the TAPT model, shown here in stars, and the hidden state Markov model, shown here in open circles, across all of the items learned during day 1. Looking across the data from the 4 different spacing conditions, a high degree of similarity of the inferences made by both models is seen. The place of most disagreement is seen in the first couple trials, and this stems from a difference in assumptions about what learning phase individuals start at. Tennyson and Anderson's hidden state Markov model assumes all individuals start at the computational phase and then move throughout the different phases. However, the TAPT model assumes that an individual can start at any of the 3 different learning phases. However, despite these differences in assumption, a high degree of intercorrelation is seen across inferences of learning phase between the 2 models, and this suggests that both models are capturing similar aspects in the data. Now looking at the comparison between the TAPT model and the predicted performance equation. Here we show that both models fit to the subject's performance during the first experimental session, here shown in the black line. Both models were able to fit the data fairly well, although the TAPT model was able to fit better relative to the predicted performance equation, here shown in red. This is better highlighted when we look at the correlation, RMSD, and the number of predicted data points that fell within each model's predicted 95% density interval across all the 4 learning conditions. The TAPT had a higher correlation, a lower RMSD, and was able to account for more data relative to the predicted performance equation. This finding by itself isn't too important since the TAPT model is more complex. We would expect that it should be able to better fit the data. However, when we look at each model's prediction of participants' performance during the second experimental session, it's found that despite the TAPT model's additional complexity, it is able to better account for participants' performance. However, the PPE consistently predicts that individuals will be slower at the start and over the course of the second experimental session. Now, taking a look at the prediction metrics for the second experimental session, it's seen that for both models, the correlations decrease and the RMSD increases as well. And this is expected because we're no longer calibrating to performance, but instead making predictions. However, in 3 of the 4 learning conditions, it's seen that the TAPT model has a lower RMSD compared to the predicted performance equation and was able to predict the data better with more data falling within each model's predicted 95% highest density interval relative to the predicted performance equation. We take this finding to suggest that TAPT's model's additional complexity is warranted because it's able to better predict out-of-sample performance from the individual. Finally, to summarize, I've presented a new model called TAPT, which is integration of 3 different previously existing models: the predicted performance equation, Tennyson and Anderson's skill acquisition model, and Lee's 2019 change detection methodology. We compared these models and their ability to account and predict performance from a learning retention study. When we compared these 3 models, we found 3 important findings. 1, we found a great amount of agreement between the inferences of learning phase between the TAPT model and Tennyson and Anderson's skill acquisition model, suggesting that both models are capturing similar patterns found in the data. And we compared the TAPT model with the predicted performance equation. We found that TAPT model was better able to calibrate to the performance data from the first experimental session and better able to predict performance on this second experimental session across the majority of the spacing conditions. This suggests that TAPT's additional complexity is warranted because we're better able to predict performance at the level of the individual learner. From these results, we propose 3 lines of future research. So 1, we would like to better examine the TAPT model's decreased accuracy in the 32-item spacing condition relative to other spacing conditions. Second, we would like to generalize this approach to more complex learning situations where individuals don't go through discrete stages, but might have to choose between more complex strategies. And 3, we would like to extend the model to account for multiple performance measures. So in these results, we only looked at response times. We could also add response times and accuracy metrics. So in conclusion, models of spacing often do not take into account the strategies and mechanisms that individuals use to solve problems, which leads into difficulties for these models to account for individual item-level variability. Our results show that these models of spacing can be improved in both their ability to calibrate and predict performance by integrating the capacity to account for discrete learning phases over time. I'd like to thank you for listening to my talk, and we'd also like to special thanks to the National Science Foundation
and ORISE, who supported this research.